I'm Misbah Sheikh from New LJ Institute of Engineering Technology presenting digital fundamental lectures. In today's lecture, I'm going to discuss about IC logic family and the classification of various IC logic family based on the fabrication used. Now, first we will see what do you mean by integration circuit. Integration circuit is nothing but a piece of semiconductor material where it contains various resistor, transistor to make a one particular circuit. Now, various integration levels here used are: first is small scale integration in which 12 gates per chips are required. Now, next is medium scale integration where 100 gates per chips are available. 100 gates per chips are required. Now, the next is large scale integration in which 1 gate, that is 1000 gates per chips are required. Now, next is very large scale integration where 100k gates per chip is there, and the next is ultra large scale integration in which 100k gates per chips is there. Now the next we will see the classification of logic family based on this fabrication used and the operational state. One is bipolar logic family, which is using transistors, resistors, diodes, etc. And the another one is unipolar logic family, that is based on the MOS, that is nothing but a metal oxide semiconductor. Now we'll see these bipolar logic families subclassified into two logic. One is saturated logic and the non-saturated logic. In saturated logic, it classified into the RTL, that is resistor transistor logic. Next is DTL, that is DTL, the diode transistor logic. TTL, that is transistor logic. DCTL, that is direct coupled transistor logic, and the high HTL, that is high threshold logic. Now in non-saturated we will be having this Schottky TTL and this ECL. ECL stands for emitter coupled logic, and the another one is unipolar logic family. The subfamilies of these unipolar logic families are this PMOS, that is P channel MOSFET, that is based on the metal oxide semiconductor field effect transistor. Next is NMOS, that is N channel MOSFET, and then the next is CMOS, that is complementary MOS, that is a combination of PMOS plus and MOS. Now we will see the characteristics. Let's see the characteristics of digital ICs. Now, first of all is power dissipation, that is nothing but a power consumed by any gate for if we provided all the inputs. Next is a propagation delay. It's average time taken by the signal to reach from input to output when the signal changes its value, and that is expressed in the nanosecond. Next is a fan out. So the gate is nothing but the number of loads that can be connected to the output of the gate without degrading its normal circuit having a XOR gate, and which is drives a 4-node gate. So the fan out of this XOR gate is 4, that you can see from the screen here, that is 4. Now the fan in, that is a number of inputs connected to the gate without degradation of any voltage level. If any circuit is having a XOR gate which is having a 3 inputs, so the fan in of this XOR gate is 3. Now is noise. Next is noise immunity. What is this noise immunity? Now whenever the signal travels from the input to output, the noise may occur. So this will add some random fluctuation to the voltage levels. So to cope up with this noise, voltage ranges defining the logic levels are more tightly coupled at the output as compared to the input. So the small amount of the noise that can be tolerated will not affect to the whole functioning of the circuit. So the maximum noise that voltage can tolerate in a circuit, that is known as a noise immunity or a noise margin. Now we will see first logic, that is saturated logic family, that is our resistor transistor logic. The device for this resistor transistor logic is NOR gate, and as its name implies, resistor transistor, so it uses resistors as well as transistor. Here the high input, that is a logic 1, and the low input, that is logic 0. Now we will see first our NOR gate truth table. If we draw a truth table for the 2 inputs, so the outputs are like this. If 0 0, the output is 1. If 0 1 or 1 0, so output is 0. If all the inputs are 1, out is 0. If we see for the OR gate 0 0, so 0 1 1 1, so is opposed to this our OR gate. The NOR gate gives our output. Now we will see first working of this our circuit. Now three inputs are there, A, B and C. Now if all the inputs are 0, so that means all these registers, all these Q1, Q2 transistors are in cutoff region. That means they are open circuit. So whatever power we supply through our resistor, this appears at the output Q. So the logic 1 will be the output when all the inputs are 0. If any of the now if any of the input is 0, so another input will be in saturation region. But after coming into saturation region, the transistors, now let's say suppose a case when if A is equal to 0, B is equal to 0, but C is equal to 1. So this Q1 and Q2, they are in cutoff region. That means they are off, Q1 and Q2. Now this C is equal to 1, so it appears into the saturation region. But here the voltage VC is appears at this Q1, that is nearly about 0.2, and that is connected to the ground. So whatever, so it is logic 0 will be appear, that is appears at the Q. So output will be 0. So if any of the output is 0, if any of the input is 0, so any of the input is 0, output will be 0. Now what about this? If all the inputs are 1, if A is equal to 1, B is equal to 1, C equal to 1, so that means all the resistors are in the saturated region, but the VC current flow to this all the resistor is equal to 0.2. So the average current flow is 0.2. So and as we can see, all these transistors are connected to the ground. So the as an output we get the logic 0. So here we can see the characteristics of this RTL. It is having a poor noise margin, poor fan out facility, high power dissipation. That means higher power consumption will be there. So due to these features, this is approximator now obsolete. Now the next is diode transistor logic. It is having a greater fan out capability and more noise margin. Now it is main device for this DTL is an NAND gate. So we have to first see the truth table for our NAND gate. Now here we are having a 2 input. So we'll see the NAND gate for the 2 input. If 0 0, here it will be 1 0 1 or 1 0, again 1 and 1 1, so 0. Now we will see the working of our circuit. If first case will be discussed, if A and B both are 0, so this D1 and D2 both the diodes will be in forward bias. So as a result, this our VCC will flow in this direction. So this R3 will be in reverse bias. So in that case, no sufficient current will be there. So that makes a Q1 on. So our Q2 is off. So whatever VCC apply, that is go through this R2 and that is appeared at our output Q. So our Q1 is 1. Now what if all the inputs are 1? So D1 and D2 both are in reverse bias. So the current will flow in this side. So R3 will be in forward bias, and as a result base current is flow through this Q1. Q1 will be turned on, but now the Q1 is connected to the ground. So the logic 0 will be appear this, and this logic 0 will appear at the output Q. So the logic the Q output will appear. Output for this is 0. So if all the inputs are 0, output 1 will be there, and if all the inputs are 1, output 0 will be there. If any of the case we will be discussed, if either A is equal to 0 and B is equal to 1, so A will be in forward bias and the D2 will be in reverse bias. Now R3 will be reverse bias, so there is no sufficient current to make a Q1 on. So whatever VCC that we apply, that is appears at output Q. So our output will be 1. So this is how this DTL works. And now whatever the disadvantage of this DTL circuit, that is Here we have to connect the number of the diodes, and the speed of the this circuit is significantly low. So we have to go for the another option.